The universe is 13.8 billion years old. It contains somewhere between 100 billion and 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. A significant fraction of those stars have planets. A significant fraction of those planets are in the right zone for liquid water. And liquid water, as far as we know, is where life begins. Run those numbers, and the conclusion seems inescapable. The universe should be teeming with life. Intelligent life. Civilizations that have had millions, maybe billions, of years head start on us. Civilizations that have had time to spread across their galaxies, build megastructures, send signals, make their presence known. So here's the question that stops physicists and astronomers cold. The question that has no satisfying answer. The question that, once you really let it sink in, is one of the most unsettling things you will ever contemplate. Where is everybody? That question is the Fermi Paradox. And the silence that answers it might be the most terrifying thing in the universe. In this video, we're going to go through all of it. We'll start with the paradox itself, what it is, where it came from, and why the math behind it should genuinely alarm you. We'll look at the conditions for life and just how many opportunities the universe has had to produce it. Then we'll work through the proposed solutions, and some of them are stranger and darker than you might expect. We'll talk about the great filter, the single most disturbing concept in all of astrobiology, and what it means for our future. We'll look at the civilizations that might exist out there and why we might not be able to see them even if they're everywhere. We'll dig into the darkest theories, the ones that suggest the universe is silent not because it's empty, but because something makes sure it stays that way. And at the end, we'll sit with the hardest possibility of all, that we might be alone. And what that means. Let's begin. The story begins in the summer of 1950 at Los Alamos National Laboratory in New Mexico. A group of physicists, including the brilliant Italian-American Enrico Fermi, one of the architects of the atomic age, were walking to lunch, talking casually about a recent cartoon that had appeared in a New Yorker magazine. The cartoon was about flying saucers. The conversation drifted, as conversations among physicists do, toward the real question. Could extraterrestrial life actually exist? Could aliens actually be out there? Fermi listened, thought for a moment, and then asked the question that would bear his name forever. But where is everybody? Sounds simple, almost flippant, but behind it was the full weight of Fermi's extraordinary mathematical intuition. He had done the rough calculation in his head. The galaxy is ancient. Stars have been forming for billions of years. If even a small fraction of them had planets, and even a small fraction of those planets developed life, and even a small fraction of that life became intelligent, and even a small fraction of that intelligence developed technology, the numbers still come out enormous. There should be countless civilizations out there. Some of them should be millions of years older than us. They should have had time to colonize the galaxy many times over. And yet, silence. No signals. No visitors. No evidence of anyone, anywhere, ever. That gap between what the numbers predict and what we actually observe is the Fermi Paradox. Not really a paradox in the strict logical sense. More like a profound, yawning mystery, a question mark the size of the observable universe. To really feel the weight of the Fermi Paradox, you need to feel the scale of the universe. And that is genuinely difficult because human brains did not evolve to comprehend numbers like these. Let's try anyway. Our galaxy, the Milky Way, contains roughly 200 to 400 billion stars. That's our galaxy alone. The observable universe contains an estimated 2 trillion galaxies. 2 trillion. Each one containing hundreds of billions of stars. The total number of stars in the observable universe is approximately 10 to the power of 24. That is a 1 followed by 24 zeros. It is more stars than there are grains of sand on every beach and desert on Earth, by a factor of about 10,000. Now, how many of those stars have planets? We used to not know. Then, starting in the 1990s, we began discovering exoplanets, planets orbiting other stars, and the numbers have been staggering. Based on what we've found, astronomers now estimate that virtually every star has at least one planet. Some have many. The Milky Way alone likely contains more than 1 trillion planets. Of those, how many are in the habitable zone, the range of distances from their star where liquid water could exist on the surface? Conservative estimates put the number in our galaxy alone at tens of billions. More optimistic estimates go higher. And life on Earth arose relatively quickly after the planet formed, within a few 100 million years, practically an eye blink in geological time, which suggests that given the right conditions, life might not be rare at all. It might be what chemistry does when you give it enough time and the right environment. The numbers scream that we should not be alone. And yet, here's what makes the Fermi Paradox so unsettling. Specifically, it's not just that we haven't found aliens. It's that we haven't found any evidence of aliens. Anywhere. Ever. Not a signal. Not an artifact. Not a megastructure. Not a pattern in the data that can't be explained by natural processes. Nothing. And given the age of the universe, that silence is deeply strange. Consider, the Milky Way is about 100,000 light-years across. A civilization that developed spacefaring capability even 1 million years ago, a blink in cosmic time, could theoretically have colonized the entire galaxy by now, even at speeds far below the speed of light. If they sent out ships at just 1% of light speed, they could cross the galaxy in 10 million years. And 10 million years is nothing. Our galaxy is 10 billion years old. So where are the colonists? Where are the probes? Where are the signals? Where is the evidence that in 10 billion years of cosmic history, in a galaxy with hundreds of billions of stars, at least one civilization arose and made its mark? The silence isn't just surprising. It's almost physically impossible to explain, unless something is very, very wrong with our assumptions. Either life is far rarer than the numbers suggest, or intelligence is rare, or something stops civilizations from expanding, or we're looking in the wrong way, or, and this is the option that keeps people up at night, something else is going on entirely. Before we can assess how common life might be, we need to think about what life actually requires. Because our only example of life is life on Earth, and it's dangerously easy to assume that what worked here is the only thing that can work anywhere. The basic requirements for life as we know it are liquid water, a source of energy, and the right chemistry, primarily carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are among the most abundant elements in the universe. Carbon in particular is a chemical superstar. It can form more types of molecules than any other element, which is why it's the backbone of biochemistry. Liquid water requires a fairly narrow range of temperatures and pressures. On Earth's surface, that means staying between 0 and 100 degrees Celsius at 1 atmosphere of pressure. Around a star, that corresponds to the habitable zone, the Goldilocks region where it's not too hot and not too cold. But here's the thing, water can be liquid in other places too. Europa, a moon of Jupiter, almost certainly has a liquid water ocean beneath its icy surface, kept liquid by tidal heating from Jupiter's gravitational pull, not by proximity to the Sun. Enceladus, a moon of Saturn, actively vents water vapor into space. Titan has liquid on its surface, not water, but liquid methane, which raises the possibility of chemistry we've never imagined. Life might not even need carbon and water. Those are the ingredients for life as we know it. Life as we don't know it, based on silicon or ammonia or exotic chemistry in exotic environments, is not ruled out by physics. We simply don't know, which means the universe might be even more hospitable to life than our conservative estimates suggest. The range of environments that could support some form of chemistry-based complexity might be far wider than we think. The number that astronomers use most often comes from the Drake equation, a formula developed by astronomer Frank Drake in 1961 to estimate the number of communicating civilizations in our galaxy. We'll come back to the Drake equation in more detail, but one of its key terms is the number of planets in the habitable zone of their stars. Based on data from the Kepler Space Telescope, which surveyed a small patch of sky and found thousands of exoplanets, astronomers estimate that roughly 20 to 50% of Sun-like stars have an Earth-sized planet in their habitable zone. In a galaxy of 2 to 400 billion stars, even the conservative end of that estimate gives you tens of billions of potentially habitable planets. Tens of billions. In one galaxy, and that's just the Sun-like stars. Red dwarf stars, the most common type of star in the galaxy, also have habitable zones, though the dynamics are different. Many red dwarf planets are tidally locked, always showing the same face to their star. Whether that allows for habitable conditions is debated. But if even a fraction of red dwarf planets are habitable, the number of candidate worlds jumps by an order of magnitude. We are not looking for a needle in a haystack. We are looking for a needle in a field the size of a continent, filled with haystacks. Before 1992, we had exactly 0 confirmed planets outside our solar system. The existence of other planetary systems was assumed but unproven. Then everything changed. The first confirmed exoplanet discoveries came in the early 1990s, orbiting a pulsar, not a typical star but a rapidly rotating neutron star. The first planet confirmed around a sun-like star came in 1995. And then the floodgates opened. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky containing about 150,000 stars and looked for the tiny dimming caused when a planet passed in front of its star. Over its mission, it confirmed more than 2,600 exoplanets and identified thousands more candidates. What Kepler found transformed our understanding of planetary systems. Planets are not rare. They are ubiquitous. They come in sizes and configurations we never anticipated: super-Earths, mini-Neptunes, hot Jupiters, planets in tight multi-planet systems, planets orbiting binary stars. The variety is staggering. And crucially, some of them are in the habitable zone. Some of them are rocky. Some of them might have atmospheres. We can't yet take pictures of their surfaces or directly detect their oceans. But we know they're there. We know they exist in enormous numbers. The discovery of exoplanets didn't solve the Fermi Paradox. It made it worse, because now we know the opportunities for life are there, which makes the silence even harder to explain. One of the oldest proposed solutions to the Fermi Paradox is that extraterrestrial civilizations have already visited Earth, just not recently. Given the age of the galaxy, it's entirely possible that a civilization arose billions of years ago, developed spacefaring technology, explored the galaxy, visited Earth when it was populated only by single-celled organisms or dinosaurs, and moved on. They wouldn't have found us interesting. There was nothing to talk to. They logged the visit, noted the primitive biology, and continued their survey. By the time we developed civilization, they had long since moved on or gone extinct or transcended into something we can't detect. This solution is not falsifiable, which is a problem scientifically. But it's also not unreasonable. If a civilization arose 5 billion years ago, their visit to early Earth would leave essentially no trace we could detect today. Geological and biological processes would have erased any evidence. The more interesting version of this idea asks, what if they left something behind? Probe, a message encoded in our DNA. A marker in the solar system designed to be found when we reached the technological level to find it. Some scientists have seriously proposed searching for exactly this: artificial structures in the solar system, anomalies in our genetic code, signals embedded in the mathematics of physics. So far, nothing. But we haven't looked very hard or very systematically. This one is simultaneously comforting and deeply unsettling. The zoo hypothesis proposes that extraterrestrial civilizations know we exist and are deliberately choosing not to contact us. They're watching, observing, keeping their distance, like wildlife rangers who study animals without disturbing them, or like the Prime Directive in Star Trek, a policy of non-interference with less advanced civilizations. Maybe there's a galactic community, and there's an agreed-upon protocol. Don't contact a civilization until it reaches a certain level of development. Maybe that level is achieving faster-than-light travel, or demonstrating peaceful coexistence, or joining some interstellar network. Until we qualify, we're behind the glass. The hypothesis has a certain logic to it. If you were an advanced civilization studying the development of intelligent life, interference would contaminate the experiment. You'd want to observe naturally, without your presence distorting the outcome. But it also requires something extraordinary: that every civilization in the galaxy agrees to this policy and enforces it perfectly. Not one rogue civilization breaks ranks and contacts us anyway. Not one alien equivalent of our own scientists who ignores the rules out of curiosity. The zoo hypothesis requires a perfectly enforced galactic consensus across billions of years and potentially millions of civilizations. That seems like a lot to ask. Here's a more prosaic solution. Space is simply too big. Even at a significant fraction of the speed of light, crossing the galaxy takes tens of thousands of years. No biological being could survive such a journey. And even signals, traveling at the speed of light, take 100,000 years to cross the Milky Way. Maybe civilizations exist, flourish, and go extinct, all within a bubble of space too small to ever contact anyone else. The distances are so vast that even a civilization that lasts 1,000,000 years, 1,000 times longer than ours so far, might only be able to meaningfully communicate with a tiny sphere of nearby stars. The universe might be full of civilizations shouting into the void, none of them close enough to another to ever hear a reply. This solution is genuinely possible, but it doesn't fully resolve the paradox because it doesn't account for the colonization argument. Even slow ships could colonize the galaxy over millions of years, and a civilization that sends out self-replicating probes, machines that mine resources from asteroids and build copies of themselves, could saturate the galaxy in a cosmically short time without any biological beings making the journey at all. Where are those probes? Most of our search for extraterrestrial intelligence has focused on radio waves. We've built large arrays of radio telescopes and listened for signals in certain frequency bands that we think a transmitting civilization might use. The famous water hole frequencies, near the natural emission frequencies of hydrogen and hydroxyl, are considered good candidates because they're quiet in space and might serve as a universal meeting point. But radio waves are a very specific technology, and we've only been using them for about 100 years. A civilization that is even 1,000 years more advanced than us might have abandoned radio communication entirely, just as we are increasingly moving away from broadcasting radio signals into space and toward targeted, fiber optic communication. A sufficiently advanced civilization might communicate in ways we haven't conceived of yet. Neutrino beams, gravitational waves, quantum entanglement, modulated pulsar signals, or technologies so far beyond our current understanding that we wouldn't recognize them as communication even if we detected them. We might be like someone standing in Times Square listening for drum signals, concluding that the city is empty because no one is drumming. This is a genuinely important caveat. Our search has been limited in scope, limited in time, and limited by our own technological assumptions. We've searched a tiny fraction of the sky, at a tiny range of frequencies, for a tiny slice of cosmic time. The absence of evidence is not evidence of absence, especially when the search has been this limited. Now we arrive at the concept that Robin Hanson introduced in 1998, and that many consider the most important and most terrifying idea in the entire Fermi Paradox discussion. The Great Filter. The argument is simple. We observe that the universe is silent. We observe that no civilization has colonized the galaxy or made its presence detectable. This means that somewhere in the journey from dead matter to galaxy-spanning civilization, there is a filter, a step that is extraordinarily difficult to pass, a barrier that almost everything fails to cross. The question is not whether the filter exists. Given the silence, it almost certainly does. The question, and this is where it gets genuinely scary, is where the filter is. Is it behind us? Or is it ahead? The optimistic scenario, relatively speaking, is that the great filter is already in our past. That we've already made it through the hardest part. What could the filter be? Candidates include the origin of life itself. The jump from simple chemistry to self-replicating molecules is still not well understood. It might be fantastically unlikely, a chemical accident that requires specific conditions and enormous amounts of time and luck. Most planets might have the right ingredients and never produce life at all. Or the filter might be the jump from simple single-celled life to complex multicellular life. For about 3 billion years, life on Earth was exclusively microbial. The jump to complex cells, eukaryotes with nuclei and mitochondria, happened only once in Earth's history, as far as we know, and the mechanism is still mysterious. Maybe it's almost impossibly rare. Or it could be the development of intelligence itself. Dinosaurs dominated Earth for 165 million years and never developed technology. Intelligence capable of building civilization might require a very specific set of biological and environmental circumstances that rarely align. If the filter is in our past, if we are the rare result of an extraordinarily unlikely chain of events, then the universe might be full of dead planets or planets with simple microbial life, or planets with complex animals that never quite made it to civilization. We got through the filter. Most didn't. We are, cosmically speaking, the lottery winners. That's uncomfortable but survivable. It means we are rare, perhaps unique, but not doomed. Now for the nightmare scenario. What if the filter isn't behind us? What if intelligent, technological civilization is actually relatively common, but almost all of them fail to survive past a certain point? What if there is something ahead of us, some threshold that civilizations almost universally fail to cross? If that's the case, then the silence of the universe is not because life is rare. It's because intelligent life reliably destroys itself or gets destroyed before it can colonize the galaxy. What could that filter be? The candidates are uncomfortably familiar: nuclear war, engineered pandemics, climate collapse, runaway artificial intelligence. Some technology that civilizations inevitably develop and inevitably misuse. Some internal dynamic of intelligent social species that makes self-destruction almost certain once a certain level of power is reached. If the filter is ahead of us, then every civilization that has ever existed in our galaxy has already encountered it and failed. We are approaching it now, and the silence of the universe is the sound of 1,000 civilizations that didn't make it past the point we're approaching. Think about where we are right now. We have nuclear weapons capable of ending civilization. We are destabilizing our climate at geological speed. We are developing artificial intelligence at a rate that outpaces our understanding of its risks. We are, by any measure, a civilization with enormous power and uncertain wisdom. If the filter is ahead, we can see it coming. We just can't be sure we'll survive it. This is the counterintuitive conclusion that Robin Hanson drew from the Great Filter argument, and it remains one of the most striking ideas in modern science communication. Most people assume that finding life on Mars would be wonderful news, evidence that life exists beyond Earth, confirmation that we're not alone, a triumph for science. But think about what it would actually mean for the Fermi Paradox. If we found microbial life on Mars, life that arose independently from life on Earth, following its own evolutionary path, it would tell us that life is not rare. That given the right conditions, chemistry reliably produces life. That in a galaxy with billions of habitable planets, life is probably everywhere. And if life is everywhere, but we still see no evidence of intelligent civilization, no signals, no megastructures, no colonization, then the filter cannot be at the origin of life. It must be somewhere else, somewhere further along the path, somewhere between microbial life and galaxy-spanning civilization. Somewhere we haven't passed yet. Finding simple life on Mars would push the Great Filter into our future. It would be evidence that the thing that kills civilizations is not the difficulty of life originating. It's something that happens after intelligence develops. Something that might be happening to us right now. The more life we find in the solar system, the more worried we should be. Not because life is dangerous, but because its presence makes the silence of the universe harder to explain in any way that doesn't implicate our own future. In 1964, Soviet astronomer Nikolai Kardashev proposed a way of classifying civilizations by their energy consumption. The idea was elegant in its simplicity. The more energy a civilization can harness, the more capable it is. And energy use scales in predictable ways as civilizations advance. A Type 1 civilization, a planetary civilization, harnesses all the energy available on its home planet. It controls its weather, manages its geology, uses every available energy source. By Kardashev's estimates, a Type 1 civilization uses about 10 to the power of 16 watts. A Type 2 civilization harnesses the full energy output of its star. The theoretical mechanism for this is a Dyson sphere, a structure that completely surrounds a star and captures all of its radiation. A Type 2 civilization uses about 10 to the power of 26 watts, 10 billion times more than a Type 1. A Type 3 civilization harnesses the energy of an entire galaxy, hundreds of billions of stars. At 10 to the power of 36 watts, this is a civilization of almost incomprehensible power. Where are we? We are a Type 0.73 by current calculations. We haven't even reached Type 1 yet. We use energy from fossil fuels, solar, nuclear, and other sources, but we don't control our climate, We don't manage geological events, and we haven't mastered our planet's energy budget. Kardashev estimated that we might reach Type 1 in a few hundred years, Type 2 in a few thousand, and Type 3 in 100,000 to 1,000,000 years. If the same trajectory applies to other civilizations, and there's no obvious reason it wouldn't, then any civilization that is even 1,000,000 years older than us should be a Type 3. A Type 3 civilization would be detectable from across the galaxy. Its energy use would leave signatures in the infrared spectrum. Its engineering would reshape star systems. It would be impossible to miss if it existed. And we've looked. We've searched for infrared excess that might indicate Dyson spheres. We've looked for anomalies in stellar behavior that might suggest engineering. We've found some candidates, including the famous Tabby star, which dims in irregular, unexplained ways. But nothing confirmed. Nothing definitive. No Type 2. No Type 3. Anywhere. Here's where speculation becomes genuinely mind-bending. Kardashev's original scale stopped at Type 3, but some theorists have extended it. A Type 4 civilization would harness the energy of the entire observable universe. A Type 5 would operate at scales beyond our current physics, manipulating dark energy, engineering the structure of spacetime itself. Carl Sagan once proposed an extension of the scale based on information rather than energy, measuring a civilization's advancement by how much information it has processed and stored. On this scale, humanity is a Type 1.0. A Type 3.0 civilization would have processed more information than can be stored in all the matter of the observable universe. What would a Type 4 or V civilization look like from the outside? The honest answer is we have no idea. They might be completely undetectable to us, not because they're hiding, but because their activities operate at scales and in modes that our instruments and concepts can't perceive. They might have transcended physical existence as we understand it, existing as patterns of information rather than matter, or manipulating dimensions of reality we haven't discovered. Or they might look like the laws of physics themselves. Some theorists have half-seriously suggested that the fundamental constants of our universe, the fine-tuned parameters we discussed in our simulation theory video, might be the engineering of a Type 5 civilization. That what we call the laws of nature might be deliberate choices made by entities so advanced they are indistinguishable from the fabric of reality itself. We wouldn't recognize them. We couldn't. They would be too far above us on the scale of development, like bacteria trying to recognize the civilization that built the petri dish. Let's focus on Type 3, because it's the most relevant to the Fermi Paradox. A Type 3 civilization has colonized or at least influenced an entire galaxy. It uses stellar energy on a massive scale. It should be detectable, unless it's not doing what we'd expect. One possibility: advanced civilizations stop expanding physically and turn inward. As computing power grows, the most interesting frontier might not be space, it might be virtual reality. A civilization that can simulate entire universes of experience might have no motivation to colonize physical star systems. Why build a physical colony when you can simulate 1,000 richer ones? If advanced civilizations migrate into simulated realities, running on small, efficient computronium nodes rather than sprawling across galaxies, they would be almost invisible. Their physical footprint would shrink as their virtual existence expanded. The galaxy would look empty from the outside while being densely populated in its informational interior. Another possibility: advanced civilizations deliberately minimize their detectable output. Not for secrecy, we'll get to that, but for efficiency. Broadcasting energy in all directions is wasteful. A mature civilization might use highly directed, efficient communication that we can't detect because it's not aimed at us. Or perhaps the most advanced civilizations do something we cannot currently imagine, which leaves signatures we cannot currently recognize. The universe might be full of evidence of advanced life, and we're looking at it every day without having the conceptual framework to understand what we're seeing. Of all the proposed solutions to the Fermi Paradox, the dark forest theory is the one that tends to produce genuine unease. It was popularized by Chinese science fiction author Liu Cixin in his three-body problem trilogy, but the underlying logic is serious enough that some scientists take it as a genuine hypothesis. The argument goes like this: every civilization needs resources to survive. Resources are finite. Therefore, every civilization is a potential threat to every other. not necessarily out of malice, but out of the fundamental logic of scarcity and survival. A civilization that knows about another civilization faces a choice: communicate and risk being destroyed if the other is hostile, or destroy the other preemptively before it can become a threat. In this framework, the optimal strategy for any civilization that discovers another is immediate, silent elimination. Not because civilizations are evil, but because the risk of not eliminating a potential competitor is existential, while the cost of eliminating one that might have been friendly is merely moral. In a universe where trust cannot be established and mistakes are fatal, ruthlessness is not a choice. It's a survival strategy. The universe, in this model, is a dark forest. Every civilization is a hunter, moving silently through the trees. Any civilization that makes noise, that broadcasts its existence, attracts the attention of hunters. The silence of the cosmos is not emptiness. It is the silence of predators. If the dark forest theory is correct, then our decades of broadcasting radio signals into space, including deliberately sending messages like the Arecibo message, were a profound mistake. We have been announcing our presence in a universe where presence gets you killed. Most scientists consider this too pessimistic. It assumes a universality of resource competition and a universality of the elimination strategy that may not apply to all possible intelligences. Cooperation is also a survival strategy. Altruism evolves. Maybe most civilizations figure that out, but maybe not all of them. This is perhaps the most sobering solution because it requires no external threat, just internal dynamics. The hypothesis is straightforward. Intelligent civilizations reliably develop the technology to destroy themselves before they develop the wisdom not to. The same intelligence that allows a species to build radio telescopes and spacecraft also allows it to build nuclear weapons and engineered pathogens. And the latter tend to be developed faster, because destruction is always easier than construction. Maybe every civilization goes through a bottleneck, a period where its destructive power vastly outpaces its political and ethical maturity. A period where it has the ability to end itself but not yet the wisdom or the institutions to prevent it. And maybe most civilizations don't make it through that bottleneck. We are in that bottleneck right now. We have nuclear weapons capable of ending civilization. We have the ability to engineer pathogens. We are developing artificial intelligence that some of the most serious researchers in the field consider an existential risk. We are altering our climate in ways that could render large portions of the planet uninhabitable. We are, by any measure, a species with extraordinary power and a spotty track record of using it wisely. If we are typical, if other civilizations go through similar transitions and most of them fail, then the galaxy is littered with the ruins of civilizations that made it to our level and no further. Planets with radio telescope arrays that stopped broadcasting a few centuries after they started, because there was no one left to operate them. The silence of the universe might not be a mystery at all. It might be a warning. This solution is speculative and somewhat strange, but it's worth taking seriously because it highlights a deep assumption in the SETI enterprise. We have been looking for signals that look like signals, structured, repetitive artificial patterns in electromagnetic radiation that clearly indicate intentional transmission. That's a reasonable starting point, but it assumes that an advanced civilization would communicate in a way recognizable to us. What if they already have and we've filed it away as background noise? Consider, the history of radio astronomy is full of unexplained signals. Signals that don't match known natural sources, that appear briefly and then vanish, that have anomalous properties that were eventually attributed to natural causes, sometimes convincingly, sometimes less so. The WOW signal of 1977 remains unexplained. Fast radio bursts, intense millisecond pulses of radio energy from cosmological distances, were discovered in 2007 and are still not fully understood. Or consider an even stranger possibility. What if communication from an advanced civilization looks nothing like radio waves? What if it's embedded in something we observe constantly, the structure of cosmic rays, the pattern of quasar emissions, the distribution of matter in the cosmic web, and we simply don't have the conceptual framework to recognize it as information? We are pattern recognition machines, but we can only recognize patterns within our existing vocabulary. A message written in a language with no connection to any human linguistic structure might be invisible to us not because it's hidden, but because we don't have the mental categories to perceive it as language at all. Contact might have already happened. We might just not know it yet. The search for extraterrestrial intelligence SETI began in earnest in 1960, when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for artificial signals. He heard nothing, but the experiment, called Project Ozma, launched a scientific discipline that has continued, with varying levels of funding and enthusiasm, ever since. The basic approach of radio SETI is to scan the sky at radio frequencies that we think might be preferred by a transmitting civilization, particularly the water-hole frequencies near 1420 MHz, the natural emission frequency of hydrogen. The logic is that any technologically advanced civilization would know about hydrogen, the most abundant element in the universe, and might use its emission frequency as a universal meeting point for communication. The challenge is enormous. The sky is vast. The frequency range is huge, and we don't know where to point the telescope, when to listen, or what exactly to listen for. It's like searching for a specific conversation in a room the size of a galaxy, when you don't know the language, the channel, or the time. SETI has also expanded beyond radio. Optical SETI looks for laser pulses, extremely brief, intense flashes of visible light that could carry information across interstellar distances with minimal energy. Some researchers look for technosignatures, indirect evidence of technology, like the chemical composition of an exoplanet's atmosphere showing industrial pollution, or the infrared signature of a Dyson sphere. Despite decades of searching, no confirmed signal has been found. But the search has been far from exhaustive. We've surveyed a small fraction of stars, at a limited range of frequencies, for a brief period of time. The absence of a confirmed signal does not mean the absence of signals. On August 15, 1977, astronomer Jerry Emmon was reviewing data from the Big Ear radio telescope at Ohio State University when he saw something extraordinary. A signal had been detected that was so anomalous, so unlike anything expected from natural sources, that Emmon circled it on the printout and wrote a single word in the margin. Wow! The signal lasted 72 seconds, the maximum time the Big Ear telescope could observe any point in the sky as Earth rotated. It was narrowband, meaning it occupied a very small slice of the radio spectrum, exactly what you'd expect from an artificial transmission rather than a natural source. It was centered near the hydrogen line frequency. It was strong, about 30 times louder than the background noise. It has never been detected again, despite multiple attempts to find it, with more sensitive instruments for longer periods aimed at the same region of sky. The WOW signal remains a one-time event. It matches the expected profile of an extraterrestrial transmission better than any other signal ever detected. And it has no confirmed natural explanation. Decades later, some researchers proposed that the WOW signal might have been caused by hydrogen clouds around comets passing through the field of view. Others have pushed back on this explanation, arguing it doesn't fully account for the signal's characteristics. The WOW signal remains the most intriguing data point in the history of SETI. Not proof of anything, but a reminder that the universe is capable of producing signals that we don't understand, and that what we don't understand deserves continued attention. The next generation of the search for extraterrestrial life is moving beyond radio, and the tools being developed are genuinely exciting. Biosignatures are chemical signs of life detectable in the atmospheres of exoplanets. When the James Webb Space Telescope observes an exoplanet passing in front of its star, it can analyze the starlight that filters through the planet's atmosphere and detect specific molecules. Oxygen, methane, ozone, water vapor, these are the signatures of biological processes on Earth. If we find similar combinations in the atmosphere of an exoplanet, it would be strong evidence of life. We haven't found them yet, but we've only just begun looking with the capability to find them. Webb is already producing atmospheric spectra of exoplanets. Over the coming decades, we will survey hundreds of worlds. The probability of finding a biosignature within our lifetimes, if life is reasonably common, is not negligible. Technosignatures go further, looking not for life but for technology. Industrial pollutants in an atmosphere that no natural process would produce. The infrared excess of a Dyson sphere capturing stellar radiation. laser pulses timed with mathematical precision, radio signals with artificial structure. The funding for technosignature research has historically been almost non-existent, a fraction of a % of the astronomy budget. But attitudes are changing. NASA has recently started taking technosignature research more seriously. Private initiatives like Breakthrough Listen are funding large-scale SETI programs with modern equipment. We are, for the first time, developing the actual capability to answer the question. Not just to listen for radio signals, but to read the atmospheric chemistry of distant worlds, to scan the sky for artificial light, to look for engineering on a stellar scale. The next few decades might be when we finally find something, or definitively don't. Let's take seriously the possibility that the answer to the Fermi Paradox is the simplest one. There is no one else. We are alone, not just in the galaxy, but possibly in the observable universe. This is the rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Joe Kirschvink. The argument is that complex, intelligent life requires not just the right chemistry, but an extraordinarily specific combination of circumstances that is vastly less common than simple life. Consider what Earth has that makes it special. A large moon which stabilizes our axial tilt and prevents wild climate swings. A giant planet, Jupiter, that acts as a gravitational shield, deflecting most large asteroid impacts away from the inner solar system. A star that is unusually stable and long-lived. A location in the galaxy far from the danger center, in a relatively quiet galactic suburb. Plate tectonics, which recycles carbon and maintains a stable climate over geological timescales. An oxygen-rich atmosphere, produced by billions of years of photosynthesis. Remove any one of these, and complex life might never have arisen. Put them together, and you have a planet that survived long enough with stable enough conditions for evolution to produce intelligence. The rare Earth hypothesis suggests that this combination is not the norm. Most planets get some of these factors. Very few get all of them. The universe might be full of microbial life, hardy, adaptable, ubiquitous, and nearly empty of the complex, multicellular, intelligent life that we represent. In this scenario, we are not the product of luck at any single step. We are the product of luck at every step, compounded over 4 billion years. The result is something genuinely rare, perhaps unique. If we are alone, if no other intelligent civilization exists anywhere in the observable universe, the implications are staggering. The observable universe contains 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The total number of potentially habitable planets is incomprehensibly large. And across all of that, across 13.8 billion years of cosmic history and 10 to the power of 24 stars, we might be it. The only minds. The only things that look up at the sky and ask questions about it. That is not a comfortable thought. It is an almost unbearably lonely one. But it's also, in a strange way, a profound one. Because if we are alone, then everything that has ever been wondered, felt, discovered, created, or loved in the history of the universe happened here. Every painting, every equation, every symphony, every act of courage, every moment of tenderness. All of it is the universe's entire inventory of experience and meaning. The cosmos looked at itself through one set of eyes, ours. And if that's true, then what we do with our civilization, whether we survive, whether we expand into the cosmos, whether we carry consciousness and culture beyond this pale blue dot, is not just important for us. It might be the most important thing that has ever happened or ever will happen in the history of the universe. If we are alone, we are not insignificant. We are everything. Whether we are alone or not, the Fermi Paradox delivers the same final message. What we do next matters enormously. If we are alone, then we are the universe's only chance to understand itself, to create meaning, to become something that lasts. Our survival and flourishing is not just a human interest, it is a cosmic one. Extinction would not just end us. It would end everything the cosmos has ever produced in the way of mind and meaning. If we are not alone, if civilizations exist but tend to destroy themselves, then we are approaching the filter. And we are the first generation that can see it coming. We know about nuclear risk, about climate change, about AI safety. We have the knowledge, if not yet the wisdom, to navigate what has killed others. And if civilizations exist and thrive, if the great filter is behind us and the galaxy is quietly full of surviving intelligences, then our task is to reach them, to become the kind of civilization that earns a place in whatever community of minds exists out there. In every scenario, the answer is the same: grow up. Fast. Wisely. Together. The universe has been silent for 13.8 billion years. It has given us no instructions, no guarantee, no roadmap. Just the silence, and the question that Fermi asked over lunch in 1950, the question that still has no answer, the question that might be the most important question ever asked. Where is everybody? Maybe the answer is waiting for us to figure out how to survive long enough to find them. Or maybe, just maybe, the answer is that the universe has been waiting for something and we are it. The first ones. The ones who get to decide what intelligence becomes in a cosmos that has never seen it before. Either way, the silence is not an answer. It's an invitation. What we do with it is up to us.